a ridiculously awesome integral. So let's solve this integral. In this, probably the first approach would be to just turn this into geometric series. So most of the time, if we see expressions like e to the power x minus 1, what we do is we divide numerator and denominator by, or multiply, let's say, by e to the power minus x, and that gives us the following geometric series formula: a by 1 minus r. Now, for x going from 0 to infinity, our modulus of e to the power minus x, this is less than 1. So that's why our r is e to the power minus x and a is e to the power minus x, and this is the infinite geometric series. So that's why we can write this as x cos x, and sum from r equals to 0 to infinity, or let's do it from 1 to infinity, and e to the power minus x times r, yeah, dx. Okay, so this is just first term will be e to the power minus x, and the ratio will also be the same. So now, proceeding further, we can now change the sum integral. We can take the sum outside and write the integral from 0 to infinity of x cos x e to the power minus x r, and then dx. Now this cos x is just the real part of, we also use this really often, that this is just a real part of e to the power ix. We can use this as well. And that gives us, this is real, this all will be real part of sum from r equals to 1 to infinity, integral from 0 to infinity, x e to the power ix e to the power minus xr dx. Now after this, we can just add the powers of e. We get real part of sum from r equals to 1 to infinity, integral from 0 to infinity, x e to the power minus x. This is just r minus I, e to the power minus x, r minus I, yeah, dx. Now this is a well-known integral. This is just the Laplace transform, let's say, integral from 0 to infinity of e to the power minus st times t to the power n. If we have such expression, the Laplace transform would be gamma n plus 1 by s to the power n plus 1. So we'll use this formula now, and that gives us, this is real part of sum from r equals to 1 to infinity. This will be gamma of 2 by r minus I to the power 2. Is that 2? Yeah, that's 2. Okay, and now next, what will be the next thing? This will be real part of sum from r equals to 1 to infinity. This is just 1. This is r square minus 2ri plus I square, that's also minus 1, and then dx. Now we can basically use the conjugate so as to make our denominator a real system from the complex system. So the conjugate will be r square minus 1 plus 2ri. Denominator, we have r square minus 1 minus 2ri multiplied by r square minus 1 plus 2ri. Yeah. And now what does that give us? Now if we just multiply the denominator, the numerator is r square minus 1 plus 2ri, and denominator is r square minus 1 whole square minus, this is 2ri square, so that's 4r square times I square, yeah, so that's minus 4r square. So minus minus will be plus now. So plus 4r square. Yeah. Now this is now okay. So now we can remove real part and only write the real part from the sum. Sum from r equals to 1 to infinity. This can be written as r square minus 1, and this will be r square minus 2r plus 1. Sorry, this will be r to the power 4 minus 2r square plus 1 plus 4r square. Yeah. And then sum from r equals to 1 to infinity. This will be r square minus 1, and this will be r to the power 4 plus 2r square plus 1. That's r square plus 1 whole r square. Yeah. Now it's getting easier than what we had initially. We have sum from r equals to 1 to infinity. This is r square plus 1 minus 2 by r square plus 1 whole square. And then this is r from 1 to infinity of 1 by r square plus 1 minus 2 by r square plus 1 whole square. Yeah. Now these are some of the standard sum formulas. Yeah. So basically, but before I go to the standard formulas, let me just simplify it somehow more. R square plus 1 minus 2 times sum from r equals to 1 to infinity 1 by r square plus 1 whole square. So that this sum be alpha 1, this sum be alpha 2, then our answer will be alpha 1 minus 2 times alpha 2. Yeah. Now this sum is a well-known. Okay. So now, okay, in diagram functions, we basically will be okay. So let me now show you how we find the sum of these expressions. Okay. Now we need to delve somehow into diagram functions. Basically, let's say we have r equals 0 to infinity 1 minus r square minus let's say x square. In this case, r is bearing and x is a number. Yeah, so in this case, x is I. For r square plus 1, x should be I. Yeah. Now for this sum, we can basically break this into partial fractions. Yeah. So we can introduce r plus x minus r minus x and 1 by 2x over here. In denominator we have r plus x, r minus x. Yeah. And then we have 1 by 2x sum from r equals to 0 to infinity. This will be 1 by r minus x minus 1 by r plus x. Yeah. Yeah. So this is going from 0 to infinity basically. Yeah. But this one is going from 1 to infinity. That's fine. Okay. Now in this case, let us take it from 1 to infinity because we need it to be from 1 to infinity for using standard diagram formulas. Yeah. If it's from 1 to infinity and if it's this sum, now this sum will be equals to digamma of x plus 1 minus digamma of minus x plus 1. So this is the property from diagram function. So basically such kind of sum will be equals to this, and the reason is simple because it's like this, because digamma of x plus 1 is negative of Euler-Masconi constant plus sum from n equals to 1 to infinity 1 by n minus 1 by n plus x. Yeah, and similarly digamma of minus x plus 1, we can just take r for this purpose. We can make it n as r equals to minus Euler-Masconi constant plus sum from n equals to 1 to infinity 1 by n minus 1 by n minus x. So you see, so basically if you subtract this from this, we get 1 by n minus x minus 1 by n plus x. So from the definition of digamma function, we can see that. Yeah. After this we have 1 by 2x, and this can be written as 1 by x plus digamma of x, because that's the property of digamma function. Yeah. And minus digamma of 1 minus x. Now we have to use reduction formula of digamma function. That gives us 1 by 2x, 1 by x minus, we can have digamma of 1 minus x minus digamma of x. And if we use the reduction formula, this is should be equals to pi cot pi x. So this is actually the sum minus pi cot pi x by 2x plus 1 by 2x square. This is actually the sum for sum going from r equals to 1 to infinity of r square minus x square. This is actually the formula. Yeah, we initially started with that thing, and so this is the formula. Yeah. And now if it is sum going from r equals to 1 to infinity, and if it is r square plus x square, in that case you need to substitute x by ix. Yeah, if you substitute x by ix, this will be I square x square, so this becomes plus. So we'll also substitute over here pi cot pi ix by, this will be 2ix plus 1 by 2 I square is minus 1, so minus x square. Yeah. And now cot of ix is minus I cot of x. Now to derive this, what we can do is, now to derive this formula, we can basically go from the definition. Basically, sorry, not cot. Okay, so sorry, this is minus I cot x. Now to derive this formula, basically cot x is cos x by sin x. Yeah, and cos x is e to the power ix plus e to the power minus ix by 2, and sin x is e to the power ix minus e to the power minus ix by 2i. So cot x is I times e to the power ix plus e to the power minus ix by e to the power ix minus e to the power minus ix. So this is the cot x. Now if we input x as ix, what we can see is I times, this will be e to the power minus x plus that will be e to the power x by, so this will be I times ix e to the power minus x. Yeah. And then this will be minus of this will be e to the power, what will be e to the power x. Yeah. Now we can see that this is I times, if we divide both by 2, both expressions by 2, this is just cos x, and this is minus sin x, because these are inverse. This is minus sin x. So you can see that cot of ix is actually minus I cot x. Yeah. So because it's minus I cot x, I have already done it over here. Now over here also we will have minus pi times minus I cot pi x by 2i x plus minus 1 by 2x square. Now I will cancel, minus minus will multiply and cancel, so we have pi cot pi x by 2x minus 1 by 2x square. So now this is the formula for this expressions that we needed. So over here in our sum, we had that expression. So this sum from r equals 1 to infinity of 1 by r square plus 1 is 1. For this, now what we need to do is just put x as 1. So let us first find this sum alpha 1, then we will go to alpha 2. Yeah, alpha 2, for alpha 2 we just need to differentiate this sum and nothing more. So now we know that this is actually equals to sum from r equals to 1 to infinity of 1 by r square plus x square. Now to find that sum, what you can do is input x as 1. Sum from r equals to 1 to infinity 1 by r square plus 1, that will be pi cot as pi by 2, and then also this is minus 1 by 2, so minus 1 by 2. So this is our alpha 1. Yeah. Now for alpha 2, what we can do is we can take that sum first. We can take that sum, yeah, that is sum from r equals to 1 to infinity of 1 by r square plus x square is equals to pi cot as pi x by 2x minus 1 by 2x square. Yeah, and now after we have that, what we can do is we can try to differentiate both sides. Yeah, we can try to differentiate both sides with respect to x. What does that give us? If we try to differentiate both sides with respect to x, here we will have minus 1 by r square plus x square whole square times 2x. Over here, we can first take 1 to common and then differentiate. So we will have x, and then derivative of numerator is pi cot as pi x. Yeah. So sorry. So pi, the derivative of cot is minus cosec square. So minus cosec x square pi x, and then using chain rule, the derivative of pi x is pi. This is v times u dash minus, now let's write the numerator, pi cot as pi x, the derivative of denominator is 1 by denominator squared x square, and then over that this is x to the power minus 2, so that's minus 2, x to the power minus 3 is 2 by x cube. Yeah. So now what we can do is we can just put x as 1 and then we'll get the sum. So r equals to 1 to infinity, we can just take the 2 out and we put x equals to 1, that gives us, okay, minus 2 outside, 1 by r square plus 1 whole square equals to 1 by 2. Yeah, and this will be, okay, so what will this be now? Minus pi cosec x square pi, okay, so minus pi square, because also there's another pi, square pi minus pi cot as pi minus 2, because x square x cube are just 1. Yeah, that's 1. And then we can take this 2 also over here, that gives us 1 by 4, and we multiply by minus sign, that gives us a sum from r equals to 1 to infinity of 1 by r square plus 1 whole square, and that gives us pi square cosec x square pi, yeah, and then plus pi cot as pi, and then plus 2. Is that correct? Am I missing something, or I had felt like the answers was somehow different. but let me just check it once. So basically both of them are in plus plus. In this last one, let us check for the sign. So b u dash minus u v dash. Okay, so I have made a mistake, I guess. Over here, I don't think I made mistake again. Wait. So this, when we differentiate, this will be plus. Yeah, because this is x to the power minus 2. So minus 2 comes in front, and minus minus gets plus. So this was the mistake, and I noticed it. No. Now after this, okay. So after this, okay. So what we have to do now? Now we just have to add all of these. So basically, okay. So what was our initial expressions over here? We have come a long way. Okay. So our initial expressions over here are alpha 1 minus 2 times alpha 2. So alpha 1 is pi cot as pi minus 1 by 2 times minus 2 times alpha 2 is this long expression, which is pi square cosec h square pi plus pi cot h pi minus 2, and then by 4 as well. So this is our alpha 2. Now after this, what we can do is we can just multiply. Yeah, we can just multiply. But does that agree? Yeah. Okay. So pi. Okay, so if you take LCM, this will just be 4. We will have 2 pi cot s pi minus 2 minus 2 pi square cosec h square pi minus 2 pi cot s pi plus 4. Yeah, we have that. Now these two cancel out, and we have, what do we have? We have so that is minus 2 pi square cosec h square pi plus 2 by 4. Yeah. Now if we take if we just cancel the 2's with 2, we will have 1 by 2 as common, and then 1 minus pi square cosec h square pi. 1 minus pi square cosec h square pi. So that is the answer. I finally solved it. And this did involve a lot of tools, and I tried going from basic into all of those. Like I derived y cot ix is minus I cot hx, and also the formulas of digamma functions and this differentiation. So this was differentiation, so digamma function, this was hyperbolic function, and this was just some normal integration techniques. First of all, we changed into geometric series and then sum, and we used real part function, and then we use Laplace transform, and then over here we also use rationalization and then partial fractions. So it involved a lot of techniques, in fact, but it was a really nice integral, and I hope you enjoyed this. And yes, thanks for watching. Look forward to seeing you in the upcoming videos.